Good morning, class, and welcome to this session. The topic for today is logical reasoning and truth tables. It's a very interesting topic, but it needs your full attention. Do all to pay much attention and replay any session that you didn't get. During the Q&A session, go ahead and ask your questions, and I'll be glad to help you out. So our goals, these are the learning goals. By the end of the session, you should be able to define propositions and identify whether a sentence is a proposition. You should also be able to interpret basic logical connectives like these ones. I will explain them as we go on. Construct a truth table for a compound statement and then use truth tables to identify tautologies and contradictions. So what's the basic concept? Here we are saying that every statement is either true or false. So we define a proposition as a statement that has a definite true value. So examples of proposition is the sky is blue. Is it true or false? The sky is blue. The answer will be either true or false. So in this case, we know the sky to be blue, so the answer is true. So once you have a statement like this that has these only two responses possible, then that statement qualifies to be a proposition. And those two responses have to be true or false. Now close the door. It's not It's a statement. It's actually a command. It's not a statement. And close the door, the response to it is not true or false. So this cannot be a proposition. It doesn't qualify as a proposition. Another example is, what time is it? That's a question. It doesn't have any truth value, whether it is true or false. So can you think about other examples of propositions and other examples of non-propositions? Okay, so an example of a proposition is ATU is in Kumasi. That is a proposition because the answer is false. It has a truth value, and the truth value is false. ATU is not in Kumasi, it is in Accra. KNUST is in Accra. That's also a proposition because the answer is false. KNUST is not in Accra, it is in Kumasi. Okay. Another example would be ATU has a canteen in the school. That also is a proposition because the it's a statement that has a truth value. It's either going to be true or false. So if you think about any statement that has a truth value and it's either true or false, then that is a proposition. If it doesn't have any truth value, it's a command, a question, then we say that it is not a proposition. Let's look at some logical connectives. Let P and Q be propositions, not P. So this symbol over here, we read it as not P. This is the symbol negation, okay, as we have here, not P. Negation, it flips the truth value of P. So P here is standing for the proposition, that statement or that sentence, which has a truth value. So if P is true, then negation of P is false. If P is originally false, then the negation of P is true. So it simply flips the truth value from false to true or from true to false. Now we have the and, which we write as this. This is and, okay? So we have P and Q. Now, P and Q is true. So this is a compound proposition. You have two statements, statement P, statement Q. P is a proposition, Q is also another proposition, and we have combined them into this compound proposition. So this is P and Q. So this compound statement P, or this compound proposition P and Q is true only if both P and Q are true. So P must be true, Q must be true for P and Q to be true. If one of them is false, then we say that the compound P and Q is also false. Now we look at or, which we write as this, and we have it here as P or Q. This is true if at least one of P or Q is true. So what we are saying is that this is also a compound proposition, P or Q. In this case, if P is true, then the entire compound is true. If Q is true, only Q is true, and even P is false, then the entire compound is true. If both P and Q are true, then the entire compound is true. So you need only one of them to be true for the entire compound to be true. Either P alone can be true, or Q alone can be true, or both of them can be true. Once only one of them is true, the entire compound is considered to be true. So both of them must be false for the entire compound to be false. Our next connective is implies like this. We write it as P implies Q. Now, P implies Q is false only when P is true and Q is false. So it is false only when the first one, the first position is true, and then the second one is false. Okay? So only when this one is true, and then the second one is false. So just in case Q was here, Q was rather here. So in this case, if it says, let's say, Q implies P, then this statement, this compound proposition is true only when Q is true and P is false. So it's only when the first one is true and the second one is false. Now we have if and only if. That is, P implies Q and Q implies P at the same time. This is true when P and Q have the same truth value. What does this mean? It means that for this statement, this compound proposition to be true, P must be true and then Q must also be true. Or P must be false and Q must also be false. So if they are true, both of them should be true at the same time. Then this compound statement can be true. Or both of them must be false at the same time. Then this compound statement will be true. So generally, we are seeing that this symbol means inclusive or unless stated otherwise. Okay. All right. So what are these connectives? These connectives just combine two or more propositions to become a compound proposition. This is the only one that does not combine a negation. It just takes a single proposition and changes its truth value, or it flips its truth value. Make sure that you pay attention to this section very well because it's the foundation for all the other ones we are looking at. So if you need to replay, do replay and make sure you understand it. So we are coming to truth tables now. A truth table is a systematic way to list all possible truth values of a compound statement based on the truth values of its components. All right, so why does it matter? It helps us compare the truth value of complex logical expressions. When we say complex logical expressions, we mean expressions that are combined. So you've combined a lot of single propositions with various logical connectives. So let's say if you have compound statements P, Q, and R, you can combine them to say P and Q or R. This is a complex logical expression. It involves a lot of propositions and then two different connectives. So you need a table to be able to find A table will help you to seamlessly find the truth value of this entire compound proposition. It also helps us test if a statement is always true or it's always false. When a statement is always true, it's a tautology. And when it's always false, it's a contradiction. It also helps us check logical validity and equivalence. Yeah. So these statements, logical validity, equivalence, we will look at them as we proceed. I will explain them. What's the purpose of truth tables? Truth tables are used to analyze the behavior of logical connectives. So are the ones we've seen previously. They're also used to verify the validity of logical arguments and then to check if really a statement is a proposition and how valid a statement is. You also use it to identify a tautology and a contradiction, and it's used to compare statements to see if they are logically equivalent. So some key definitions are tautology. Now, a tautology is a statement that is true for all truth value assignments. So if you look at a tautology, if you have a table, all the possible truth values you see there will be true, 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 true. Once all the final truth values are all true, we call that statement a tautology. Once all the final statements are false, we call that statement a contradiction. So a statement that is false for all truth value assignments. How to construct a truth table? To create a truth table for a compound statement, you first of all list the simple statements. So for example, we have the statements P, Q, and R. Then determine the number of rows that you need. How do you determine the number of rows? Take note of this expression here. Determine the number of rows with 2 raised to the power n, where n is the number of simple statements. So once there are three simple statements, P, Q, and R, then we have 2 raised to the power n. N is equal to 3. So if there are 3 statements involved, like P, Q, and R, you put 3 in place of n. So 2 raised to the power 3 is I mean 2 raised to the power 3, for example, we have equals 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, which means that you are expected to have 8 rows. As you are drawing the table, these are rows, so please take note. Your rows are these. This is 1 row, 2 rows, 3 rows, 4 rows, 5 rows. So once you have 3 statements like this, you're expected to have 8 rows in your table. Then you fill the truth values in a systematic pattern. Don't overspeed. So fill truth values in a systematic pattern. We'll look at it. Then you compute the intermediate columns. So let's just go straight into working it out. Truth value patterns for P and Q. So just in case you have two statements, P and Q, how do you write out the truth value? Remember, there should be four rows because 2 raised to the power n, and n is equal to 2, is 2 times 2, and that's equal to 4. So you first of all start by writing, you write your P here and then your Q here. Then you draw a line like that. So you have P has this column, Q has this column. So how do you start? Now for these two, if you're combining them, let me start with just P. I'm going to write, it should have 4 rows, right? So P is equal to true, P is equal to true, P equals false, P equals false. Now for Q, I'm going to, rather instead of doing true, true, false, false, I'll do true, false, true, false. You will notice that I've exhausted all the possible values. Because if you're combining P and Q, it's either P is true and Q is true, or P is true and Q is false, or P is false and Q is true, or P is false and Q is false. So these are the 4 possibilities. If you have 2 statements like that, either both of them are true or both of them are false, or this P is true and this Q is false, or the Q is false and then the P is true. These are the 4 options you can have with 2 statements regarding their truth values. And that's what we have here. So the pattern, how did I come about this? I had to just use a system to ensure that I get all the possibilities out. Instead of listing it true, 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 false, false, true, false, false. If the table is very long, if there are 3 or 4 statements, and you don't have a systematic way of writing, the way I wrote true, true, and then false, false for P, and then true, false for Q. If I didn't do it that way, I could have missed out some pattern. And especially if you have a lot of statements. So here's a pattern idea. P stays the same for 2 rows, then switches. But Q alternates every row, and that's what I did. Now construct the truth table for P implies Q. P implies Q. So we use the first, what we did in the previous slide, this one. We have to start with that because this table or this question involves 2 propositions. So this session, this session is what we did previously. So we want to solve the P implies Q session. And remember, we said in the previous slides that P implies Q is false only when P is true and Q is false. It is false only when P is true and Q is false. So when you're doing a table like that, you just look for where P is true and Q is false. Put your false there like this. Then every other place put true. You just write true, true, true. Because once P is true and Q is true, P implies Q is true. Once P is false and Q is true, P implies Q is true. Once P is false and Q is false, P implies Q is true. So it is false only when the first one is true and the second one is false. That is when it's false. Every other instance for P implies Q is going to be true. So the reason is P implies Q is false only when P is true and Q is false. Notice that it's not just P, always P being true and Q being false. It's the first one. In this case, the first one is P. So once the first proposition is true and the second one is false, then the entire compound statement is false. Every other instance is going to be true. For example, when P is true and Q is true, it is true. When P is false and Q is false, it is true. When P is false and Q is true, it is true. Then another example. Construct the truth table for P and Q into brackets implies P. So this question still involves two statements. So you're expected to have 2 raised to the power 2 rows. That is 4 rows. And as you can see, we have 1, 2, 3, 4, 4 rows. You start by listing out, as we have already done, the various truth options for P and Q, which is the left-hand side here of the green line I've drawn, okay? So now you see it's a compound statement, but it's in levels. So we do what's in bracket first, then we proceed to finish up. So what's in bracket is P and Q. Now we know that for P and Q is true only when both P and Q are true. Every other instance is false. So once P is true and Q is true, P and Q is true. Every other case, let's say P is true, Q is false. P is false, Q is true. Both of them are false. In these all three cases, P and Q is false. It's true only when both of them are true. So we have been able to find the truth values for P and Q. So we're going to take P and Q to be a new statement. It's a new compound statement. Let me call it R, okay? So we're going to say R. What is R? Implies P. What is R implies P? R is here and P is here. So we'll look at it that way. Don't be confused, okay? But because the first example I'm solving, I'm going to bring out R and I'll bring out P so you don't get confused. But you could do it straight away. So what is R? R stands for P and Q, which is true, false, false, false. This is R. This R implies P. So I go back for P and I take P. P is what? True, true, false, false. So then, what will be R implies P? Remember, R is standing for P and Q. I have just chosen R to make it simplified. So what's going to be R implies P from here? We know for R implies P, it is false only when the first one is true and the second one is false. So we have true, true, therefore R implies P is true. False, true is true. True, false. False, false is true. False, false is true. So because we didn't have we didn't have where R is T and P is false. This would have been the only case that R implies P would have been false. But we don't have any such situation. So you realize that it's all true. And now that we have all of this to be true, we are saying that the statement R implies P is a tautology. If you recall, we said that once all the possible outcomes, truth values of the particular statement is true, we call it a tautology. So in this case, P and Q implies P is a tautology because all the values here are true. So you've seen an example of a tautology displayed out right before you. This is what I have been talking about previously. Yeah. That's an example for you to practice. Construct truth tables for the following. Show intermediate columns. So you go through it step by step by step. Identify which of them are tautologies and which of them are contradictions. I'll do the first one with you and then you do the rest on your own. So you have to do it step by step by step. Okay. So we want to do the truth value of the first one is negation of P or Q. I'll start by drawing my table. P, Q. Okay. First of all, I see negation of P or Q. So I'm going to first of all do the negation of P. So negation of P, let me first of all fill in the truth values of P or Q. We have true, true, false, false, and then true, false, true, false. Okay. So negation of P is if P is true, the negation of P is false. If P is true, negation of P is false. If P is false, negation of P is true. If P is false, negation of P is true. So you're looking at you're flipping the truth value of P. So now I want to look at negation of P or Q. Now remember, we can go back with the or case. It is false only when both of them are false. If only one of them is true, then the whole statement is true. If both of them are true, the whole statement is true. So let's look at it. These are the two rules we are considering. Negation of P and Q, okay? Q is true, P is false, so it's true. Q is false, P is false, so this is false because both of them are false. Q is true, negation of P is true, so we have it as true. Q is false, negation of P is true. Once negation of P is true, it is true. So this is the outcome. The final response is negation of P or Q is true, false, true, true. Now, this is the way the flow is depending on how you listed out this first two columns. So if you're true, true, if you're, let's say, true, false, fill here, you still should have 3 truths and 1 false. And they must correspond to the exact P truth value and the exact Q truth value. Okay. That's why it's always good to follow the systematic way of filling out the P column and the Q column. So we have this here as our final response for negation of P or Q. All right. So let's try number 2 and number 3. Remember, if you have brackets, do your brackets first. Then you combine your brackets. You can use a new variable to represent your bracket. So look at number 4, for example. You can do P implies Q first. You present it by, let's say, R. Do Q implies P. Represent it by W. Then now combine R and then create a new column for R and W. Then you we find the truth values. Then that will be it. You'd have combined everything. Okay. So you create a new. Let me demonstrate for number 4 especially. So number 4, if you want to try number 4, what you do is, as usual, create for P and Q. So we have true, true, false, false, true, false, true, false. Okay. So first of all, I'm going to do what's in brackets. So I'm going to first of all find for P implies Q. Okay. Then I draw a column. Then I find for Q implies P. Then I do a column. Then I want my P implies Q, for example, to be R and this one to be W. So I'll do a column and I'll do R and W, which I'll be focusing on these 2 columns and fill up here too. Once I finish this column, I'm done. So that's how you go about them step by step. So are these propositions? 7 is an odd number. It is, because the answer is true or false, and answer is true. Number 2, study hard. It's neither true nor false. It's just a command. Accra is the capital city of Ghana. That is a proposition because it has a true statement. It's either true or false. So this is true. It's a proposition. This is a proposition. What is your name? It is not a proposition because it has no truth value. Okay, so commands and questions are not propositions. That was a quick check. So here's a summary of what we have done. We have looked at these connectives, negation, and, or, implies, and, if and only if. I've thoroughly explained what these negations mean in the previous examples that we have looked at, where we had if P is true and false, then negation of P is false when P is true and true when P is false. So in the form of a statement, look at this. If P is true, the negation of P is a statement. If P is a statement, the weather is sunny. Then negating the statement, we say the weather is not sunny. Okay. But if P is false, then the original statement for this, so the statement is actually the weather is funny. The weather is sunny. Okay. So once P is false, then we are saying that the weather is not sunny. So negation of P then will be what? The P statement is saying the weather is sunny. So the negation of P, which is P is equal to false, is the weather is not sunny. All right, yeah. So by look at it, if P is true, then negation of P is false. If P is false, negation of P is true. So it just changes the truth value, not the meaning of the words. It just switches the value, the statement from being true to false. So this is an example here. Write the following. Write the following in words. So try it and then tell me what you got during our Q&A session. Write a negation of the following statements. Statement 1, statement 2, and statement 3. Make sure you write it and share responses. Here's a conjunction and. We have looked at an example of this previously, where we drew our P and Q, and this is P. We drew the statement for P and the statement for Q. We've seen their combination, their possible combinations, and then now we have P and Q. And we know that P and Q is true only when both when both statements, that is P and Q, are true. So in this case, P is true, Q is true, then P and Q is true. Once one of them is false, or both of them are false, P and Q is false. So it's false here, false here, false here, because at least one of the statements is false, or both of them are false. Now here's a statement. P says, I study, and Q says, I pass. Then P and Q means I study and I pass. Okay, remember this stands for and. So the compound statement is true only when I study and I pass. The compound statement, if either I do not study or I do not pass, the entire statement is false. For an example is for you. P is I attend class, Q is I do the homework. Write P and Q in words and then list the only cases when P and Q is true. So try this also and then give me your response in class. Let's look at the disjunction, the or. We said previously that for or, once even one of them is true, the whole compound statement is true. It's false only when both statements are false. So as you can see, when P is true and Q is true, it's true. Once P is true, even though Q is false, it's still true. Once Q is true, even though P is false, it's still true. When both of them are false, then this is false. The only condition under which P or Q is false is when both of them are false. Here's an example. P, it rains. Q says, I bring an umbrella. So the combined statement is it rains or I bring an umbrella because this statement stands for or. So the statement is false only when it does not rain and I do not bring an umbrella. Once one of them is true, the compound statement is true. So here's an example for you to try. For each pair of statement, write the inclusive or statement and state whether it is false and state when it is false. Okay. So write a combined statement and state whether it is false, as done here. Okay. This is the implied. P implies Q. And we've said that for P implies Q, It is false only when the first one is true and the second one is false. So once P is true and Q is false, then P implies Q is false. Every other statement, every other situation or instance, P implies Q is true. So when P is true and Q is true, it is true. When the first one is false and the second one is even true, it is still considered true. When the first one is false, second is false, it is true. So here's an example. The implication P implies Q can be read as if P then Q. So P implies Q. Therefore, Q is guaranteed whenever P happens. Okay? If P happens, Q must happen. That is why if P happens and Q does not happen, then this statement is wrong. Because once P happens, Q must happen. Since Q is guaranteed, it means Q has to happen once P happens. Okay. So why is if F is false and F implies if Q is P is false and Q is false, why is it still true? Well, because when P is false, the statement if P then Q is not violated. That is what we are saying is true. Because when P is false, all right, we are saying here that the only condition that P implies Q. Okay. The only condition that P implies Q is false is when P is true and Q is false. Only this case that will give this compound statement to be false. Okay. Let me write it well. I'm not writing it well. So when P Q, P implies Q. When P is true and Q is false, then this is false. This is the only condition. Why? When P happens, Q must happen. So once P happens and Q does not happen, then this statement is false. It cannot be. But if let's say P is false and Q is false, P did not even happen, no. So we haven't even violated the statement. Nothing has happened. We have not violated the statement P implies Q. That is why it is still true. It means that this statement is still accurate. It has not been violated because P is false. It means P did not even happen. So there's Q, whether Q happens or not is not our business. Because it's only when P happens and Q does not happen that this statement is violated. Once P happens, Q must happen. So when P is T and Q is T, then this is true. All right. And when P is false, we don't care because the P didn't even happen. So the statement doesn't care at all. It is not violated. That is why FF is still true and then FT is still true. Because remember, P didn't happen, so we don't care what happens to Q. But when P happens, we care what happens to Q. Because when P happens, Q must happen. If Q does not happen, then the statement is false. All right. So here's an example. It says I study, and then P is I study, Q is I pass. So then P implies Q means if I study, then I pass. So the statement is false only if I study and I do not pass. So it means that from this statement, it is guaranteed that when you study, you must pass. So if you study and you do not pass, then this statement is false. The statement has been violated. But if you do not study, whether you pass or you don't pass, we don't care. The statement does not care. It's not violated because the first thing that must happen is you must study and you did not study. So at that point, the statement does not care what happens to you. So the statement is not violated, so the statement is still true. This is an example for you to cry. Then the if and only if condition. For this one, we are saying that P implies Q. It is true only when both of them have the same truth value. So P and Q must be true. Then P implies Q or Q implies P is also true. So it's only when they have the same truth value. So once P is true and Q is true, then Q implies P is also true. Once both of them are false, in this case, when both of them are false, then this combined statement is also true. If only one of them is, if they have different truth values, one is true, one is false, then the statement is false. Okay. So both statements must have the same truth value for this to be true. So P, if and only if Q, means that both directions hold. Note that P, if and only if Q, is equivalent to P implies Q and Q implies P. So here it means P is implying Q and Q is also implying P at the same time. So here's an example. I study, I pass. I study if and only if I pass. The statement is true when I study and I pass, TT, or I do not study and I do not pass, FF. Okay. All right. Then the statement is true. So here's an example for you to try. Do well to try it and then give me your feedback. So here are examples of compound statements, various compound statements we can look at, and we'll look at this in our next session. Thank you for being in today's session. I will see you in the next session. Make sure you put down your questions while you are going through this session so you can ask them when in class.